What are the chances that two stars flare into naked eye brilliance, two powerful earthquakes rip through Venezuela, and an interstellar traveler gets battered by a solar storm, all inside the same 72 hours? If this were pitched in Hollywood, most script editors would toss it out as far too contrived. Yet, this isn't fiction. This was reality, unfolding in late September 2025 with a level of synchronization that defies ordinary odds. Even the most skeptical minds are beginning to wonder whether coincidence alone can explain what just played out across sky and earth. Tonight, we'll walk through these events with precision, breaking down the science of exploding stars, restless tectonic plates, and turbulent solar storms before stepping into the uneasy zone where chance and patterns start to blur. Stick around until the end, because what unfolded this September may shift the way we think about what's happening above our heads. Part 1. A chain of cosmic fireworks. In less than 3 days, two stars erupted into novas, two quakes shook Venezuela, and an interstellar visitor wandered straight into the path of a coronal mass ejection. September 23rd to 21st, 2025, delivered a sequence so tightly clustered that many began to ask, was the universe trying to tell us something? Let's chart it out. On September 23rd, astronomers recorded a stellar outburst, V1935 Centauri, a nova in the southern constellation Centaurus, suddenly blazed bright enough for human eyes to glimpse at magnitude. Only days later, another star followed, V1794 Sagittari, in the Archer constellation, peaked at magnitude. Two stars, two explosions, two sudden pinpricks of brilliance on the same sky canvas. Meanwhile, Earth was making its own headlines. On September 24th at 22:21 UTC, a magnitude 6.2 earthquake struck 24 kilometers east-northeast of Men Grande in Venezuela's Zulia state. Its shallow depth of 7.8 kilometers amplified the shaking, rattling homes across Venezuela and neighboring Colombia. But Earth wasn't done. Hours later, at 03:51 UTC, on September 21st, a second quake, magnitude 6.3, struck almost the same spot, this time deeper, 14 kilometers below the surface. Twin novas, twin quake, and hovering above, satellites were tracking yet another force, massive eruptions of magnetized plasma from the sun, coronal mass ejections, CMEs, hurtling outward at over 1 million miles per hour. What made this storm unique was its trajectory. Forecasters realized the plasma clouds were brushing past 3I Atlas, the third confirmed interstellar object ever spotted passing through our solar system. The timeline reads like a stage play. Two novas erupt, twin quakes crack the ground, CMEs sweep the solar system just as an alien visitor threads the inner orbits, and all of this between September 23rd and 21st. Let's zoom out. The novas flared in Centaurus and Sagittarius, constellations visible mainly from the southern hemisphere. Their light traveled thousands of years only to reach us this week. The earthquakes rocked Venezuela, right at the fault line where the Caribbean and South American plates grind past each other. The solar storm spanned the inner heliosphere, a bubble of space stretching beyond Jupiter's orbit. And 3I Atlas, discovered just 2 months earlier by the Asteroid Terrestrial Impact Last Alert System, ATLAS, happened to be crossing the ecliptic plane near Mars and the Sun. Are these events connected? The U.S. Geological Survey insists there's no evidence linking space weather to earthquakes. Solar physicists remind us that CMEs are routine for an active sun, and astronomers say novas, while unpredictable in timing, are expected outcomes of binary star systems. Still, this level of overlap is extraordinary. Here's why this week was truly historic. 3I Atlas is only the third interstellar object humans have ever tracked, after Oumuamua in 2017 and Borisov in 2019. And unlike its predecessors, Atlas is passing through during the sun's stormy peak, solar maximum. We know what CMEs can do to ordinary comets, like in 2007, when ESA's stereo satellites filmed a solar storm ripping the ion tail clean off Comet Encke. But we've never seen one collide with a body born in another star system. The coming months promise a front row seat. On October 3rd, Atlas will skim within 28 million kilometers of Mars, giving orbiters like ESA's ExoMars and NASA's Mars Reconnaissance Orbiter a golden chance to study its nucleus and Comet in detail. On October 29th, it swings closest to the Sun, perihelion, still beyond Earth's orbit, but close enough for powerful ground telescopes to capture its secrets. On December 19th, it passes 1.8 AU from Earth, closer than Mars at its farthest opening observation windows for pros and amateurs alike. This all happens just as Earth enters a season notorious for wild space weather. The autumn equinox aligns Earth's magnetic field in ways that amplify solar storms, a phenomenon known as the Russell-McPherson effect. That's why September through November often brings the strongest auroras and geomagnetic disturbance. Here's my promise: I'll separate hard science from speculation. You'll know what's proven, what's theoretical, and what's pure what if. Because the data matters, and so does the wonder. Sometimes the most honest statement science can make is we don't know yet, but we're watching. So let's pose the big question. If CMEs can strip the tails from comets that have circled the Sun for millennia, what might they do to a wanderer forged around another star, carrying ices and dust from a birthplace light years away? That's where we're headed next. We'll dive into the twin novas that lit up southern skies, eruptions that arrived just as Earth's crust began to crack. Part 2. The double nova explosions in the southern skies. In the pre-dawn darkness of September 23rd, amateur astronomer John Seach, perched at his observatory on Chatsworth Island in New South Wales, was scanning the skies for stellar fireworks. He's been doing this for decades, waiting for faint stars to suddenly blaze. That morning, he found one. A star in Centaurus, invisible the night before, had leapt to magnitude 5.8. Just bright enough to be seen without binoculars under clear dark skies. Its name, VIR 1935. Seach's report raced across the astronomical community, triggering satellites to swing their eyes skyward. NASA's Fermi Gamma Ray Space Telescope picked up high-energy photons, blasting from the nova. The Swift Observatory pivoted to capture X-rays surging from the same region. This wasn't just a pretty twinkle, this was matter being accelerated to near light speed, magnetic fields twisting, shockwaves heating gas to millions of degrees. And then, as if the cosmos wanted to double down, another star erupted days later, V7994 Sagittarii, blazing to magnitude 6.2 in Sagittarius. Two novas, two explosions, both spotted by the same dedicated observer, both erupting within days. To put this in perspective, novas happen a dozen or so times per year across our galaxy, but too bright enough for naked eye viewing in the same week. That's exceedingly rare. The last time something similar happened was 2023, and before that, years earlier. The mechanics behind these outbursts tell a story of stellar cannibalism. Each nova begins with a white dwarf, the collapsed core of a dead star, Earth-sized but with the mass of our Sun. Orbiting with a companion star, the white dwarf steals hydrogen from its partner's outer layer. Over centuries, gas piles up on its surface, until pressure and heat ignite a runaway thermonuclear blast. The explosion doesn't destroy the white dwarf, it simply blows off the outer shell, resetting the process, until the cycle repeats. VIR 1935 Centauri stood out because of its gamma and X-ray profile. The shockwaves hurled particles into extreme energies, creating the high-energy photons Fermi and Swift recorded. It's the same physics seen in supernova remnants and black hole jets, nature's particle accelerators operating across the galaxy. For Southern Hemisphere observers, both novas were prime targets, sitting high in the night sky. Northern stargazers, by contrast, struggled to catch glimpses low on their southern horizon. Seach's discovery reports, filed through the International Astronomical Union, triggered confirmation circulars and follow-up observations worldwide. Professional telescopes began spectroscopy, while amateurs logged nightly brightness data to track the nova's fading light curves. Novas often dim over weeks or months, but not always smoothly. Some grow dust clouds that temporarily block their own light, others brighten again in multiple peaks. Watching these changes helps astronomers decode the physics of stellar explosions. And while scientists insist these novas, thousands of light-years away, have zero influence on Earth's tectonics or solar storms, the timing remains uncanny. Two novas, two quakes, and one interstellar visitor, all colliding in the same week. Science calls it coincidence. Many of us can't help but call it something closer to cosmic poetry. But Earth wasn't finished with its performance. Because just as these stars erupted above, the crust of Venezuela began to rupture below. Part 3. Venezuela, shaken. At exactly 22:21:55 UTC, On September 24, 2025, the crust beneath Venezuela's Zulia state fractured violently. The magnitude 6.2 earthquake, shallow at only 7.8 kilometers deep, unleashed energy equivalent to several nuclear detonations. Seismic waves radiated at 6 kilometers SARS, shaking homes within seconds. From Maracaibo to Caracas, from Colombian border towns to Caribbean coasts, millions felt the jolt. Videos flooded social media, chandeliers swinging, windows rattling, crowds evacuating into streets as alarms blared. But the Earth wasn't finished. Just 5 hours later, at 03:51:39 UTC, on September 25, the ground tore open again. This second quake, magnitude 6.3, originated 14 kilometers underground, in nearly the same spot, overlapping the rupture zone of the first. For context, a 6.3 releases about double the energy of a combined. These twin shocks equaled the power of a single quake, around 6.4–6.5, significant by global standards. Together they ranked as the strongest seismic activity Venezuela had seen since the devastating magnitude 7.8 Kamchatka quake on September 24, 25. Double strike secured its place among the world's most notable seismic events of late. The sequence of aftershocks carried its own tension. On September 25, UTC, a magnitude 5.8 earthquake shook the very same region, aligning with the familiar Amore decay sequence that scientists expect after major ruptures. While 5.8 may sound mild when compared to the earlier large quakes, such strength is still capable of inflicting new structural damage and prolonging fear among communities already rattled by 2 major seismic events. The tectonic backdrop of this region explains why it is so prone to strong earthquakes. The Maracaibo Basin lies inside a tangled zone where the Caribbean plate grinds relentlessly against the South American plate, forming a lattice of fault systems such as the Bocano system and the Yucano-Santa Marta fault zones. These geological divisions accumulate tension over long timescales, years, decades, or even centuries, eventually releasing their stored energy through sudden slips that manifest as earthquakes. A critical difference between the 2 primary events was their depth, one at roughly 7.8 kilometers and the other at about 14 kilometers. Depth plays a defining role in shaking intensity. Shallow quakes unleash stronger surface accelerations because seismic waves have less distance to disperse and weaken before reaching the surface. The shallowness of the September 24 event likely amplified the widespread reports of intense ground motion felt across both Venezuela and Colombia. Different international monitoring centers reported slightly varied magnitudes for these events, showcasing the intricacies of earthquake measurement. The U.S. Geological Survey initially listed the first quake at 6.2, while the European Mediterranean Seismological Center and other global networks gave values ranging from. Such discrepancies stem from multiple factors, measurement techniques, updates as more seismic station data arrive, and the use of different scales like moment magnitude, body wave magnitude, or surface wave magnitude. But beyond numbers and statistics, the human impact was undeniable. Thousands of residents, especially those in tall apartment blocks swaying for extended periods, were forced to evacuate. Emergency response teams fanned out quickly, inspecting damage and ensuring vital infrastructure like hospitals, power plants, and bridges remained functional. Although early assessments suggested damage was relatively limited for quakes of this scale, inspectors continued their surveys for days, documenting both visible destruction and possible hidden structural weaknesses that could pose long-term risks. History shows this region has always been seismically restless. The dynamic plate boundary near Lake Maracaibo consistently generates earthquake activity, though events of this size happen sporadically. Geological evidence suggests that one major rupture can sometimes redistribute stress, increasing the chance of new activity on nearby fault segments, a process known as stress transfer. This raised a pressing question: would larger quakes follow? Statistically, aftershocks are normal, often striking within days or weeks of the main shock. Yet seismologists cannot guarantee whether an even stronger quake might occur soon afterward. Despite decades of study into early warning signs, stress mapping, and probabilistic forecasting, reliable short-term earthquake prediction continues to elude science. Global seismic networks meticulously tracked each aftershock, assembling a picture of how the regional fault system responded to the stress changes triggered by the twin ruptures. Databases such as the Global Centroid Moment Tensor Project began publishing detailed analyses of rupture mechanics, fault orientations, and slip directions, shedding light on precisely which fault segments gave way and how stress is redistributed across the region. For residents of Zulia State and beyond, the double strike was a powerful reminder of their precarious geological reality. Earthquake-resistant building codes, preparedness drills, and community response systems were all put to the test. That damage reports were not worse may reflect both fortunate timing. The quakes occurred when many people were at home rather than in crowded workplaces, and steady improvements in construction practices and emergency readiness. Another intriguing angle emerged: the timing of these seismic events in relation to other remarkable phenomena unfolding the very same week. Scientists emphasized that no proven physical mechanism links solar storms, space weather, or cosmic events to earthquakes. The U.S. Geological Survey maintains a firm stance that supposed connections between solar activity and seismicity remain speculative, despite recurring claims in media and occasional research papers. Still, human nature gravitates toward pattern recognition. With twin novae, twin earthquakes, heightened solar activity, and an interstellar visitor all clustering within days, the coincidence felt loaded with meaning. The more cautious scientific perspective is to carefully document timelines, analyze each phenomenon independently, and remain open to future discoveries, while resisting the urge to assign causation where only correlation is evident. As Venezuela's communities continued feeling aftershocks, the stage was shifting skyward. The sun was preparing its own spectacular display, reminding us that our planet's surface upheavals are only one part of the drama playing out in our cosmic neighborhood. Part 4: Solar Firestorm. 93 million miles overhead, even as Venezuelan soil trembled, our star erupted with its own violence. Across those same days, while novae lit up southern skies and earthquakes split South American ground, the sun hurled massive coronal mass ejections, billion-ton blasts of charged plasma that intersected with something humanity had never observed before. An interstellar traveler. Coronal mass ejections, or CMEs, rank among the most energetic forces in the solar system. They originate in the sun's outer corona when magnetic fields twist, tangle, and finally snap like overstressed cords. This process of magnetic reconnection unleashes energy equivalent to billions of nuclear warheads, flinging superheated plasma outward at speeds of 253,000 kilometers. NASA's Space Weather Prediction Center models these storms using WSA and LEL, a powerful computer simulation that tracks CME paths across the helios. By factoring in solar wind speeds, plasma density, and magnetic orientation, the model forecasts how these storms will interact with planets, spacecraft, or other celestial bodies. Late September 2025, the NLAL model projected multiple CMEs sweeping through the inner solar system. The very weak twin novae and twin earthquakes made headlines. What set this moment apart was historic. For the first time, a solar storm was predicted to collide with an object not native to our solar system. The interstellar visitor, designated 3I Atlas and discovered only months earlier, was threading its way through the inner heliosphere during solar cycle 20. Moving on a steep retrograde orbit tilted nearly 75 degrees against the ecliptic, Atlas was crossing the same orbital zone where Earth resides, prime territory for solar weather encounters. We already know what happens when CMEs slam into comets. This isn't guesswork, it's documented science. In 2007, the European Space Agency's Stereo spacecraft captured a CME snapping the ion tail of Comet Encke in real time. The violent disconnection lasted hours, showing how solar plasma can shred a comet's magnetic tether and leave the tail drifting away before a new one reformed. Comets sprout two kinds of tails: the dust tail, curving away under sunlight's gentle pressure, and the ion tail, pointing straight outward along solar magnetic field lines. When a CME disturbs those magnetic linkages, the ion tail can detach entirely, vanishing into space as the comet builds a replacement from fresh outgassed material. For 3I Atlas, model forecasts hinted that a CME sideswipe was possible in late September. While this conclusion came from trajectory modeling rather than direct imaging, the implications were exciting. If true, astronomers expected changes, a brighter coma from heightened ionization, distortions in the ion tail captured in telescopes, or chemical fingerprints in spectra, as solar energy vaporized molecules, like CO and CN from its ancient ice. Amateur astronomers played a critical role here. Global networks of observers contribute nightly images, which, when compared over time, can reveal subtle shifts in brightness, tail shape, or coma structure that even professional observatories might miss. The physics behind these interactions echoes the very processes that drive solar flares and geomagnetic storms. As solar plasma collides with a comet's ionosphere, tangled magnetic fields can link, break, and reconnect, releasing bursts of energy that accelerate particles and spark visible changes. Its magnetic topology transforming in real time, turning stored field energy into motion and light. 3I Atlas was more than just another cometary visitor. It was only the third confirmed interstellar object ever detected, following. Unlike its predecessors, however, Atlas lingered near the ecliptic plane, placing it squarely in the path of concentrated solar weather. And unlike Oumuamua's fast high-inclination flyby, Atlas's trajectory increased its odds of direct CME encounters. Solar cycle 25, at peak during 2024-2025, provided exactly the kind of stormy backdrop that could make such interactions observable. With sunspot counts climbing, flares more frequent, and CMEs erupting often, the timing put Atlas on a collision course with the Sun at its most volatile. Confirming a CME impact required ongoing analysis, brightness monitoring, spectroscopic shifts, and morphological changes studied over hours and days. Observatories, both professional and amateur, kept watch, though early results remained tentative. The broader implications were immense. If the Sun could visibly alter an interstellar body, it meant we were witnessing cosmic interactions that echo across the galaxy. Other stars surely produce their own CMEs, which could shape the behavior of wandering objects passing through their system. Atlas itself may already carry signatures of such encounters from past journeys across interstellar space. By the close of September 2025, the overlap of stellar outbursts, terrestrial earthquakes, solar storms, and an interstellar flyby created a timeline so dense with extraordinary events, it tested our sense of coincidence. Were these just random overlaps, or hints of deeper patterns? That question lingered as Atlas moved onward, heading toward a close pass by Mars on October 3, possibly carrying the marks of its brush with our tempestuous Sun. Part 5, Framing the Uncanny. Pause for a moment and look at the tapestry we've laid out. Twin novae blazing into view, twin quakes splitting South America, CMEs roaring through the solar system, and an interstellar wanderer moving through our cosmic backyard, all packed into the final week of September. It was a week when the universe felt unusually crowded with meaning. This is where science and human perception collide, sometimes uncomfortably. Our brains evolved to seek patterns, the rustle that might reveal a predator, the sky shift that could signal rain, the subtle cues hinting at social danger or opportunity. That instinct to connect dots has been key to survival, but it can also mislead us into seeing significance in random clusters. The scientific consensus urges caution. Seismologists stress that no demonstrated causal link ties solar activity to earthquake. After decades of research, no correlation has proven reliable enough to make predictions. Earthquake forecasting, whether based on local signals or cosmic influences, remains beyond our reach. Astronomers view novae not as cosmic surprises, but as predictable outcomes of binary star evolution, when white dwarfs siphon material from companion stars until a runaway nuclear ignition occurs. Their timing follows astrophysical rules, not solar system happening. The twin novae of late September 2025, V1935 Centauri and V79 Sagittarii, were dramatic but not mysterious within stellar physics. Solar scientists likewise see coronal mass ejections as the natural result of tangled fields in the Sun's corona, particularly frequent during solar maximum. That late 2025 produced multiple CMEs was not unexpected, but entirely in line with cycle statistics, and the observed interactions between CMEs and cometary material, also firmly in the realm of established plasma physics, supported by decades of spacecraft imaging and peer-reviewed research. Accepting mainstream scientific explanations doesn't mean we should ignore the extraordinary timing of this unusual cluster of events. At times, the cosmos seems to arrange circumstances so closely that coincidence begins to feel like synchronicity. Even if the underlying processes remain entirely natural, we're left asking, how do we balance rigorous skepticism with a sense of wonder? That balance will guide us here, keeping a clear line between what instruments confirm, what models explain, and what remains speculative curiosity. Our foundation rests on measurable facts, magnitude values from seismographs, coordinates logged by observatories, detections across spectra from satellites and ground-based telescopes. These are the raw recordings, the undeniable signatures of nature's activity. On that solid base, we layer scientific interpretation, drawing on proven physics and long-tested models to explain what unfolded. Beyond that, we may carefully step into the speculative, considering potential connections between solar storms and earthquakes, pondering whether stellar outbursts can ripple into solar system dynamics, or imagining mechanisms that might link cosmic phenomena to geological responses. But these will be treated for what they are, hypotheses, not established truths. To keep clarity, we'll define the vocabulary at play. A nova occurs when a white dwarf in Anusatif undergoes runaway fusion on its surface, causing the system to brighten by thousands or millions of times. It differs from a supernova, which obliterates the star entirely. A coronal mass ejection, or CME, is a colossal eruption of plasma and magnetic fields from the Sun, traveling hundreds to thousands of kilometers per second. Perihelion refers to an object's closest approach to the Sun in its orbit. One astronomical unit, the average Earth-Sun distance, equals about 93 million miles, or 50 million kilometers. A comet's iron tail forms when solar wind strips electrons from gases in the coma, creating charged particles that stream straight outward along magnetic field lines. These tails can stretch millions of kilometers, making invisible solar interactions visible to the eye. With those definitions in place, we can separate hard evidence from imagined links without dismissing curiosity. Our journey will examine the physics of stellar eruptions, the rupturing of Earth's crust, and the solar storms coursing through interplanetary space. We'll follow the path of 3II Atlas during its Mars encounter on October 3rd and its close solar approach on October. Along the way, we'll explore legitimate hypotheses about cosmic terrestrial links and clearly flag more exotic possibilities as speculation. Seasonal influences add another layer. Around the autumn equinox, Earth's orientation enhances geomagnetic coupling with the solar wind, a process called the Russell-McPherson effect. This geometry often intensifies space weather in September and October, offering one more reason why late September showed elevated solar activity independent of any link to other cosmic events. The object 3II Atlas stands out not just because it's only our third confirmed interstellar visitor, but because it arrived during heightened solar unrest. Its orbit carried it close to the ecliptic plane, where most solar system dynamics occur, maximizing opportunities for multiple spacecraft and observatories to capture its behavior under solar influence. Unlike Oumuamua, which sped away before it could be deeply studied, or Borisov, which stayed at greater distances, Atlas lingered in a region of heavy solar interaction, offering months of observation. The stakes of October and November went beyond astronomy textbook. Missions orbiting Mars, ESA's ExoMars Trace Gas Orbiter and NASA's Mars Reconnaissance Orbiter, prepared opportunistic observations of Atlas during its October 3rd flyby. Their instruments promised an unprecedented look at the nucleus and coma of an interstellar body. At the same time, ground-based telescopes worldwide tracked its brightness, chemical changes, and shifting morphology, hoping to see how solar storms sculpted matter from beyond our solar system. Meanwhile, seismic networks in Venezuela remained on alert. Aftershocks can continue for weeks or even months following large ruptures, and while no one can forecast whether a bigger quake might strike, continuous monitoring helps chart how stress redistributes across regional faults. The Caribbean-South American plate boundary is inherently unstable, ensuring that seismic activity will remain a feature of the region, though the timing of each release remains beyond prediction. Our promise here is honesty, to give priority to explanations grounded in observation and physics, while still acknowledging speculative ideas clearly and respectfully. The human drive to seek meaning in patterns deserves recognition, even when science finds no causal thread. Perhaps the most astonishing aspect of this convergence lies in its timing. We live in the first era where humanity can simultaneously track interstellar objects, monitor quakes in real time, watch novae explode across the spectrum, and follow solar storms as they ripple through the solar system. Ancient peoples might have seen bright stars flare or felt the earth tremble, but they could not connect these dots across space and time. Today, with global networks and orbiting observatories, that gives us the ability to distinguish between what is observed and what is imagined, what is proven and what is possible, what is likely and what is only conceivable. With that framework in mind, we turn to the physics behind one of the most mysterious stellar phenomena: how stars can explode spectacularly without destroying themselves. Part 6. Anatomy of a nova. Imagine a white dwarf, a stellar core compressed into a sphere no larger than Earth, but weighing as much as our Sun. Its gravity squeezes matter to densities nearly 1,000,000 times that of water, while surface temperatures soar around 50,000 degrees Fahrenheit. This stellar remnant is what remains after a sun-like star expels its outer layers and collapses into degenerate matter, where atoms exist in states impossible on Earth. Now envision that white dwarf locked in orbit with a companion star, perhaps a red giant whose swollen atmosphere spills material outward. The white dwarf's gravity siphons this hydrogen, drawing it across space in streams that spiral inward, like water circling a drain. Layer by layer, this stolen gas builds on the dwarf's surface, compressed by immense gravity into ever denser and hotter conditions. For decades, centuries or longer, the material piles up. Eventually, as the temperature nears 100 million Kelvin, the pressure ignites runaway nuclear fusion. In seconds, an explosive reaction sweeps through the accumulated layer, releasing energy equal to thousands of years of the sun's normal output. Yet the white dwarf itself survives. The blast expels only its borrowed envelope, leaving the core intact to begin the process anew. This cycle explains why V1935 Centauri's eruption drew such attention. Space telescopes recorded the event in multiple wavelengths. NASA's Fermi Observatory detected gamma rays, while Swift picked up hard X-rays, evidence of electrons spiraling through magnetic fields at incredible energy. These findings reveal novae as natural particle accelerators, launching protons and electrons at velocities rivaling those achieved in Earth's most advanced lab. The nova's ejected shell, expanding at thousands of kilometers per second, slams into the interstellar medium, driving shockwaves that energize particles and light up the spectrum. Amateur astronomers also played a vital role, submitting thousands of brightness estimates through the American Association of Variable Star Observers. Their continuous monitoring filled gaps left by professional instruments, creating a detailed light curve that charted V1935 Centauri's rise, peak, and gradual decline. A nova's brightness typically climbs over days or weeks, sometimes reaching naked eye visibility. Peak luminosity may linger briefly or persist for months, depending on the white dwarf's mass and the fuel supply. The fading phase can take months or years, occasionally punctuated by secondary surges. Spectroscopy shows the changing composition of the ejector, early broad lines of hydrogen and helium narrowing over time, later giving way to faint forbidden transitions possible only in ultra-thin gases. These September novae are V1935 Centauri and V7994 Sagittari, are likely several thousand light-years away, meaning the light we observed in 2025 left its source when human civilizations were just discovering agriculture. We witnessed events that actually unfolded millennia ago, timed to reach Earth in a week already packed with celestial and terrestrial upheaval, Even modest equipment can capture these displays. A DSLR with a telephoto lens can record novae during bright phases, while small telescopes allow visual observers to estimate their magnitude. CCD-equipped astronomers contribute even finer photometry, supplementing professional datasets. The naming system follows astronomical convention. V marks a variable star, followed by its catalog number. Thus V 1935 Centauri is the 1031st variable, classified in Centaurus. Another layer of intrigue comes months later, when some novae form dust. As ejected gas cools, grains condense and obscure the star's light, causing dramatic dimming before dispersing or evaporating under radiation. These so-called dust dips add complexity to nova evolution, making them laboratories for cosmic chemistry. Despite their violence, novae release only a fraction of the energy of a supernova. A single eruption may match the sun's output over 10,000 years, but supernovae can eclipse entire galaxies. Still, some white dwarfs experience recurrent novae, exploding every few decades as they steadily accumulate mass. If they near the Chandrasekhar limit, the maximum mass a white dwarf can hold, they may eventually cross the threshold into a type Ia supernova. Observatories worldwide continue monitoring the September novae across multiple wavelengths. Hubble could capture high-resolution images of their shells, while radio arrays track synchrotron emission. Classifying them as classical novae rests on spectral evidence and light curves, distinguishing them from dwarf novae or luminous red novae, caused by other mechanisms. Yet open questions remain. V 1935 Centauri's gamma-ray output places it among a growing class of high-energy novae that defy traditional models, hinting at physics that bridges the gap toward more extreme stellar phenomena. As we studied these explosions across the cosmos, Earth itself reminded us that our own planet carries energy and violence comparable in its own way. Just as stars rupture in bursts of light, the crust beneath Venezuela prepared to demonstrate how sudden and powerful terrestrial forces can. Part 7, Anatomy of a Quake Cluster. Beneath Lake Maracaibo and the surrounding Zulia state, lies one of South America's most intricate tectonic zones. Here the Caribbean plate grinds against the South American plate, fracturing into multiple fault systems. The Bocono Fault cutting northeast to southwest through the Venezuelan Andes, the Oca Ancón Fault, stretching east-west, near the coast, and the Santa Marta Fault, extending into Colombia. Each system steadily accumulates strain over decades, storing potential energy that eventually breaks free in sudden earthquakes. The 6.2 magnitude quake that struck at 22:21 UTC on September 24 began with rupture along one such fault, about 7.8. At that shallow depth, seismic waves had little chance to dissipate before reaching the surface, amplifying shaking across the region. The rupture likely stretched several kilometers, shifting the ground by meters in an instant, releasing decades of pent-up stress. Seismic waves rippled outward at about 6 kilometers per second. The first to arrive at monitoring stations were primary, or P waves, compressional pulses, that jolt the ground back and forth. Secondary, or S waves, followed, shaking side to side, the motion most responsible for damaging buildings. Surface waves, slower moving, but often the most destructive, created the rolling ground motion that eyewitnesses described, lasting minutes in some places. Just 5.5 hours later, at 0351 UTC on September 25th, another major rupture hit nearly the same zone. This second quake measured magnitude 6.3, originating 14 kilometers below the surface, deeper than the first, but still shallow enough to generate powerful shaking. Evidence suggests this event ruptured a neighboring fault segment, its trigger likely linked to the stress redistribution from the earlier quake. This is how stress transfer works. When one fault slips, the surrounding stress field changes. Some adjacent areas are pushed closer to failure, while others are relieved temporarily. The September 24th rupture appears to have loaded strain onto the segment that finally gave way just hours later. On paper, the difference between magnitude 6.2 and 6.3 looks minor, but because the magnitude scale is logarithmic, the second event unleashed nearly twice the energy of the first. Combined, the pair released the equivalent of a single magnitude 6.4-6.5 event, ranking among the most powerful seismic releases worldwide in late September 20. International monitoring centers reported slightly different magnitudes for both quakes, reflecting how measurement methods vary. The U.S. Geological Survey favors the moment magnitude scale calculated from the total energy released. The European Mediterranean Seismological Center sometimes uses scales based on surface or body wave amplitude. As more seismograph data is processed, numbers get refined, which is why media headlines listed ranges like 6.1 to 6.3 for the first rupture. The aftershock sequence fit long-established pattern. A magnitude 5.8 jolt on September 25th was a typical large aftershock, smaller than the main shocks, but still strong enough to cause disruption. Omori's law, formulated in the early 20th century, describes how aftershock frequency decays over time, many in the first days tapering to smaller, less frequent events that can persist for months or even years. The human toll extended across Venezuela and into Colombia. The shallow depths amplified surface shaking, prompting high-rise evacuations in multiple cities. Social media rapidly filled with clips of swaying lamps, rattling glass, and panic stairwell evacuations as emergency protocols kicked in. While immediate damage reports appeared limited for quakes of this size, survey teams spent days inspecting buildings for both visible cracks and subtler, long-term weakening that could pose risks in future tremors. The region's tectonic architecture explains the repeated violence. The Maracaibo Basin formed through collisions and interactions between the Caribbean and South American plates, creating a tangled web of faults that constantly adjust to ongoing motion. Lake Maracaibo itself lies in a graben, a downdropped block bordered by active normal fault. The same tectonic forces that produced the petroleum-rich sedimentary basins also continue to drive seismic unrest. Depth estimates, always tricky in complex geology, place the first quake around 7.8 kilometers. These depths anchor both events in the brittle upper crust, where rock fractures abruptly instead of deforming plastically. The close succession raised the question, could external factors have played a role? Could solar activity, atmospheric changes, or space weather act as triggers? The consensus view, reaffirmed by the USGS and global seismological organizations, is no reliable correlation exists. Decades of studies find no predictive links between solar flares, CMEs, geomagnetic storms, and seismic activity. At best, atmospheric pressure changes or earth tides shift fault stresses by tiny amounts, detectable only with sensitive instruments, and far too small to trigger ruptures, unless the fault was already on the knife's edge of failure. More insight came from the Global Centroid Moment Tensor database, which provides detailed analyses of rupture mechanics, which fault planes slipped, their orientations, and slip direction. These beach ball diagrams reveal the regional stress field, helping researchers map where stress has been added and where future risk might rise. In terms of forecasting, only statistical methods exist. After major quakes, the probability of additional large ones increases for weeks to months, but never with precise timing or location. Building resilience is therefore the first defense. In Venezuela's Zulia state, building codes and preparedness systems were once again put to the test. The relatively moderate damage was partly luck, but also a sign of progress in construction standards. Still, older structures remain vulnerable, and history shows this region is capable of far stronger quakes. Faults around Lake Maracaibo have produced magnitude 7 events before, and geologists agree they will again, though whether in days, decades, or centuries remains unknowable. The Venezuelan sequence reminded us how solid Earth operates. Tectonic plates creep along at centimeters per year, quietly storing strain. Then in mere seconds, that stored energy is released in violent waves of motion. As aftershocks continued along the Caribbean's South American boundary, attention shifted skyward to the Sun, where another kind of colossal energy release was reaching its own peak. Part 8, the Sun at maximum. Solar cycle 25 hit its apex in 2024-2025, transforming the usually stable star into a tempestuous powerhouse, capable of ejecting billion-ton clouds of plasma across the solar system. On September 24th and 25th, The same days that Venezuelan ground shook, southern skies glowed with stellar eruptions as solar activity indices climbed to extreme levels. One key measure, the 10.7 centimeter radio flux, hovered around 180-190 solar flux units in late September. This daily reading, taken by radio telescopes, strongly correlates with the number and activity of sunspot regions. Anything above 150 indicates high solar activity, above 200 signals very active conditions, ripe for major space weather events. Sunspots themselves tell the story of magnetic turmoil. These dark patches, sometimes larger than Earth, mark where magnetic fields burst through the solar surface and choke convective heat flow. Within sunspot cores, fields can reach 3000 Gauss, about 6,000 times Earth's surface field strength. More sunspots mean more opportunities for tangled magnetic lines to reconnect explosively, driving solar flares and coronal mass ejections. CME. During solar maximum, the Sun's global magnetic field loses its neat dipole form, twisting into a chaotic mesh. Active regions, sprawling sunspot groups, linked by magnetic loops, can persist for weeks as they rotate across the solar disk, occasionally flaring in spectacular fashion, visible throughout the solar system. CMEs are the most dramatic of these eruptions. When stressed field lines in the corona snap and realign, magnetic energy transforms into kinetic, launching massive plasma clouds outward at speeds from NOAA's Space Weather Prediction Center tracks them using the WSA in-Lyell model, a 3D simulation mapping solar wind conditions and CME trajectories through the heliosphere. Though effective for broad predictions, the model cannot capture every intricate structure or behavior of a CME. Adding to the intensity, the autumn equinox enhances geomagnetic coupling through the Russell-McFerran effect. This alignment makes Earth's magnetosphere more receptive to reconnection, so even moderate CMEs can trigger strong geomagnetic storms in September and October. The impacts extend far beyond dazzling auroras. Geomagnetic storms can scramble high-frequency radio links vital to aviation and shipping, force satellites into corrective maneuvers due to atmospheric drag, and in severe cases, destabilize power grids with induced current. To manage this, NOAA maintains storm scales, the G scale for geomagnetic activity, S scale for radiation storms, and R scale for radio blackouts. Comets add another dimension. Their ion tails, made when solar wind strips electrons from coma gases, forming charged particles that stretch millions of kilometers, serve as natural plasma laboratories. When a CME slams into a comet, the effects can be stunning. In 2001, ESA's Stereo spacecraft recorded a CME severing Comet Encke's ion tail, which drifted away while a new tail formed from fresh material. Such encounters vividly illustrate the dynamic nature of solar-comet interaction. For 3I Atlas, our third confirmed interstellar visitor, timing could not have been more dramatic. Unlike its predecessors, Oumuamua and Borisov, which traversed quieter solar cycles, Atlas entered the inner system amid peak solar unrest. Its path along the ecliptic, the busy plane where solar activity is most concentrated, maximized chances of direct interaction with CMEs. The physics of CME travel involves magneto-hydrodynamics across staggering scales, from particle motions to shock fronts, spanning planetary orbits. Fast CMEs often overtake slower solar winds, creating compression zones that accelerate particles. Multiple eruptions can collide, merging into superstorms, or twisting fields into complex reconnection events. To monitor this chaos, professionals draw on a suite of space. NASA's Solar Dynamics Observatory provides continuous EUV imaging of the solar surface. SO peers from its L1 vantage to spot far-side eruptions. AC, also at L1, delivers early warnings of incoming solar wind. On Earth, amateur radio operators double as citizen scientists, logging real-time HF propagation changes that reveal storm effects across the ionosphere. Cycle 25 appears to be following a double-peaked pattern, with strong activity in 20. This extended maximum suggests heightened space weather risks may persist well into 20. Public fascination has surged, with aurora chasers sharing stunning displays of green, red and violet skies from polar regions on social media. These lights are the atmospheric fingerprints of solar storms. Oxygen and nitrogen atoms glowing as they release energy absorbed from charged particles. The solar wind itself carries embedded magnetic fields, stretched into vast interplanetary lines, connecting planets, comets, and spacecraft, all the way to the heliopause, the boundary where solar influence finally balances interstellar pressure, 100 times farther from the Sun than Earth. As September 2025 closed, forecasters and skywatchers alike focused on one object, threading through this stormy system, an interstellar visitor, 3I Atlas, on its way to a historic encounter with another world. In the quiet early hours of July 1, 2025, the asteroid terrestrial impacts the last alert system, better known as Atlas, picked up an unusual object drifting against the starfield. At first glance, it looked like just another faint comet, but within days, orbital analysis revealed something far more extraordinary. This wasn't a typical solar system body, it was an interstellar traveler. The object was soon confirmed as only the third visitor from another star system ever observed by humanity, following the enigmatic Oumuamua in 2017. Its official designation, 3I Atlas, tells its story. The 3I marks it as the third catalogued interstellar object, while Atlas honors the survey telescope that caught sight of it first. Unlike its predecessors, this new wanderer arrived under near-perfect circumstances. It was bright enough to study in detail, moving along the ecliptic plane, the very region where most solar system bodies reside, and doing so right in the midst of the solar maximum. This combination created an unprecedented chance to explore how our restless sun interacts with a piece of material forged around a distant star. The visitor's orbit revealed its alien pedigree instantly. Rather than the closed ellipse of a bound comet, its path was hyperbolic, with an eccentricity far greater than 1. In simple terms, it had too much speed to ever be captured by the sun's gravity. Even more striking was its steep inclination of about 75, meaning it cuts through the solar system on a retrograde path, moving in the opposite direction to the planets, against the normal flow of traffic. As for size, models place 3I Atlas somewhere between several hundred meters and perhaps as much as 15 kilometers wide. But these numbers carry wide margins of error. Even the largest telescopes on Earth cannot directly resolve its nucleus. Instead, astronomers see only a tiny star-like blur wrapped in a faint shroud of gas and dust. Size estimates therefore hinge on assumptions about its surface reflectivity, composition, and level of outgassing, unknown factors for an object formed under entirely foreign conditions. A major milestone looms on October 3, 2025, when the interstellar Voyager will pass just 0.19 astronomical units from Mars, roughly 28 to 30 million kilometers. This close brush offers an unprecedented observational opportunity, with a fleet of orbiters already stationed around the red planet. ESA's ExoMars Trace Gas Orbiter and NASA's Mars Reconnaissance Orbiter are among the spacecraft poised to capture front-row data from the cosmic encounter. Astronomer Avi Loeb likened the moment to a blind date between a world of our solar system and a traveler from the star. Instruments like the highest camera aboard MRO, which can resolve objects just 30 centimeters across on the Martian surface, will achieve a scale of about 30 kilometers per pixel when trained on. While that's too coarse to reveal nucleus details, it could still show whether the object maintains a dense compact core or appears as a more diffuse cloud. But imaging is only part of the value. Spectroscopy during the Mars flyby may detect the chemical fingerprint of gases venting from the nucleus, molecules like cyanogen, CN, carbon monoxide, CO, and carbon dioxide, CO2. These would provide rare clues about the chemistry of its home system, frozen into the object since birth. Meanwhile, amateur astronomers worldwide are contributing observations of their own. Early reports suggest the comet has been brightening faster than expected as it nears the Sun. Its southerly position favors observers in the southern hemisphere, but even northern stargazers can track it during pre-dawn hours. Organized campaigns led by groups such as the American Association of Variable Star Observers and the Minor Planet Center are coordinating global efforts, building light curves, monitoring tail development, and studying how its spectrum evolved. The timeline of close approaches stretches across months. After skimming past Mars in early October, 3I Atlas heads toward perihelion on October 29th, when it will pass the Sun at 1.36 to 1 astronomical units outside Earth's orbit, but still within reach of both ground-based and space-based telescopes. Then, on December 19th, it will make its nearest approach to Earth at about 1.8 astronomical units, or 270 million kilometers. For perspective, that's closer than Mars at its farthest point from Earth, meaning the object will be well placed for continued study into early. Its behavior near perihelion may reveal whether interstellar objects act like familiar comets or display unique traits. As solar heat awakens long-frozen ices, the release of volatiles could trigger outbursts, rapid brightening, and new tail structures, possibly unlike anything seen in solar system comets. One of the most fascinating aspects is its tail morphology. Professional telescopes have captured classic ion tails pointing directly away from the sun, while some amateur observers report odd, forward-pointing dust features that appear to defy normal comet physics. In reality, these are likely the result of viewing geometry and the distinct forces acting on dust versus plasma. Dust tails emerge under the steady push of radiation pressure, sunlight nudging tiny grains into long, graceful curves, influenced by gravity and perspective. Ion tails, on the other hand, are sculpted by the solar wind, charged particles stripped from the Comet latch onto the sun's magnetic field lines and stream outward in narrow straight beams that can shift direction as the field fluctuates. Together, these tails provide a dynamic visual record of the interplay between the sun and the visitor. Still, fundamental uncertainties remain. Even the most powerful instruments cannot directly resolve such a small, distant body. Estimates of size depend heavily on its albedo, how reflective its surface is, and on how active it becomes. Some reports have speculated that it could span up to 15 kilometers, but such claims must be treated carefully until refined with thermal emission data and brightness modeling. The amount of gas and dust it produces, relative to its size, also skews brightness, making it an unreliable proxy for dimensions. As if this weren't enough, October 2025 will also deliver another showpiece. While 3i Atlas steals headlines as the rarest of visitors, a second celestial player is set to appear, Comet C. Discovered in September 2025 by amateur astronomer Vladimir Beazugli, while scanning public SO1 data, this comet races toward a spectacular mid-October, showing potentially bright enough to be seen with the naked eye. Beazugli's discovery story highlights the role of citizen science. SOS-1 instrument maps hydrogen in the heliosphere, and by carefully comparing successive frames, he spotted a brightening point that didn't match any known comet. Quick analysis revealed it was indeed a long-period comet, making its first known trip through the inner solar system. Comet Swan reached perihelion on September 12, just days after being spotted. As it drew closer to the sun, it brightened dramatically, textbook behavior for a fresh comet shedding ancient ices. The geometry of its orbit makes October an ideal time to view it. Initially best placed for southern observers, it shifts into better position for northern skies as the month progresses, just in time for its closest approach to Earth on October 12. If predictions hold, Comet Swan could peak at magnitude 4 to 6, visible to the naked eye under dark skies, and dazzling through binoculars. Yet, as with all comets, forecasts are notoriously unreliable. Some comets brighten spectacularly, exceeding expectations and forming breathtaking tails, while others fade, fragment, or underperform. Swan's newcomer status makes it especially unpredictable. October offers a rare alignment of cosmic events. The new moon falls on the 20th, 21st, removing lunar glare. The Orionid meteor shower peaks on those same nights, adding streaks of Halley's Comet debris to the sky. Meanwhile, both 3i Atlas and Swan will be active, meaning skywatchers could witness two comets, a meteor shower and a pristine night sky, all at once. Though both comets contain similar ingredients, water ice, carbon monoxide, carbon dioxide, organics, their origins are starkly different. Swan condensed in the early solar system, likely spending billions of years in the distant Oort cloud, before being nudged inward. 3i Atlas, by contrast, formed in another star system entirely, carrying chemical and structural signatures of alien origin. The double display creates unique scientific and photographic opportunities. Wide-field images could capture both objects in the same frame, revealing their distinct tails. Time-lapse sequences may show how each evolves under varying solar wind conditions. Professional facilities, including the Hubble Space Telescope, may secure detailed images, while amateurs around the world will add brightness and morphology data to the collective record. For casual observers, Binoculars often give the most rewarding views, showing the nucleus, coma, and tail in a single frame. Dedicated comet chasers use CCD cameras and spectroscopy to log subtle changes in structure and chemistry. Together, these efforts promise to turn October 2025 into one of the most memorable months in modern astronomy. Radio telescopes stand as one of the most powerful tools for unlocking the secrets of passing comets. By tuning into specific molecular emission lines, they can expose the chemistry hidden in the expanding coma, tracing everything from water and carbon monoxide to more complex organics. These signals also hint at the temperature structure of the gas as it flows outward, painting a layered picture of a comet's evolving atmosphere. Unlike solar or lunar eclipses, observing comets carries virtually no risks to human health. There is no danger of eye damage, no need for specialized filters, and no hidden hazards in simply looking up. The only real safety concerns come from the environment, navigating to dark sky sites, dealing with unpredictable autumn weather, and enduring long, cold nights outdoors with sensitive equipment. For many amateur astronomers, October skies test not just patience, but also gear durability in brisk conditions. Yet the challenges are far outweighed by the opportunities. When two striking comets appear in the same season under near-ideal visibility, educators, schools, and astronomy clubs seize the chance. Public viewing nights spring up, telescopes are aimed skyward, and people of all ages get their first introduction to comet science. Side by side, two celestial visitors with utterly different backstories, one interstellar, one born in our solar system, offer an unparalleled comparison. These shared experiences nurture scientific curiosity while reminding us that some of the universe's grandest spectacles require nothing more than stepping outside and gazing upward. As the calendar moves toward October 2025, anticipation builds for what may be one of the most extraordinary months in recent astronomical memory. On the docket, an alien comet passing Mars, a long-period comet climbing toward peak brilliance, intensified solar activity, feeding spectacular space weather, and the continued echoes of Venezuelan seismic events. The convergence of these seemingly unrelated threads, geology, solar physics, and interstellar dynamics, creates a tapestry that feels almost scripted in its timing. To make sense of this clustering, it helps to lay out the sequence clearly. On September 23, Nova V 1935 Centauri erupts suddenly to naked eye visibility. Just one day later, on September 24, Venezuela is rocked by a magnitude. Barely a day passes before, on September 25, Nova V 7994 Sagittarii explodes into prominence, while yet another magnitude 6.3 quake rattles the same Venezuelan region. A powerful 5.8 aftershock follows just 5.5 hours later. Meanwhile, late September space weather models forecast coronal mass ejections, threading dangerously close to the trajectory of 3I-8. 2 weeks later, on October 20th, 21st, Comet Swan sweeps past Earth during the new moon, perfectly timed with the Orionid meteor shower peak. Finally, on October 29th, 3I-8 reaches perihelion, brushing the sun at once. Taken together, this compression of dramatic events, stellar detonations, seismic ruptures, solar storms, and interstellar passages constructs a storyline that seems more like myth than reality. Two stars erupt in brilliance within days. Twin quakes tear through the same fault zone within hours. Solar tempests stir as a comet from beyond the solar system drifts through. A second comet brightens just in time for meteor showers. It feels like the universe itself has orchestrated a moment of resonance. This sensation taps into a deeply human trait, the instinct to perceive patterns. Our ancestors evolved in environments where survival often depended on linking subtle signs to outcomes, storm clouds to rainfall, animal movements to predator threats, or seasonal shifts to crop cycles. That same architecture in our brains still works relentlessly, scanning for connections that might suggest hidden meaning. Psychologists call this tendency apophenia, the perception of meaningful patterns in random data. It is at once a gift and a vulnerability, guiding discovery in some cases, while misleading us in others. Mainstream science remains cautious. The Geological Survey has long maintained that there is no physical mechanism linking solar storms to seismic activity, and decades of research confirm no consistent correlation. Seismologists stress that earthquakes remain stubbornly unpredictable, unaffected by solar flares, geomagnetic indices, or planetary alignments. Meanwhile, stellar astronomers remind us that novae like V1935 Centauri and V79 Sagittarii are expected outcomes of binary star evolution, igniting when white dwarfs draw enough material from their partners to trigger runaway fusion. These explosions are governed by well-understood astrophysics, not by earthly tremors or solar gusts. Similarly, solar physicists frame the season's coronal mass ejections as a predictable feature of solar maximum. Magnetic fields in the corona twist and snap more frequently during these peaks, launching charged plasma into space. It just so happens that 2025 is one such active cycle, making multiple CMEs statistically likely. And the dramatic dance between solar winds and cometary tails follows the rules of plasma physics, not cosmic fate. Still, even while science separates coincidence from causation, the clustering itself is remarkable. Sometimes random events bunch together in ways that mimic design, creating moments that feel almost poetic. The challenge lies in holding two truths at once, respecting rigorous skepticism while allowing room for wonder. We can acknowledge that twin novae appearing in the same week is uncommon without declaring them portents. We can recognize aftershocks in Venezuela as the natural progression of tectonic strain without assigning them celestial cause. We can marvel at an interstellar comet's appearance during solar maximum without believing it to be a message. Complicating things further is the amplification of modern media. In a world of instant news and viral posts, simultaneous events become amplified into a narrative of cosmic drama. The sensation of everything happening at once is heightened by coverage cycles that stack dramatic headlines back to back. What might statistically be unremarkable clustering instead feels like a cosmic script. Of course, this is nothing new. For millennia, humans have turned to the skies, seeking meaning in coincidence. Ancient cultures treated comets as omens of doom, eclipses as divine warnings, and earthquakes coinciding with celestial events as messages from the gods. That urge persists today, reframed through social media memes and modern myth-making. Balancing science and symbolism, then, becomes the task. We can interpret comets as archetypes of change and upheaval, earthquakes as emblems of the Earth's restlessness, and novae as symbols of cosmic rebirth, without confusing metaphor for mechanism. Science gives us the comfort of causality, myth gives us the poetry of meaning. Both have their place provided we keep their boundaries clear. Ultimately, the autumn equinox itself provides context without mysticism. The Russell-McFerrin effect ensures that geomagnetic disturbances peak around March and September, statistically biasing late 2025 towards stronger space weather. Similarly, subtle seasonal variations in seismicity may exist, though their causes remain debated and their effects minor. Add in our psychological pattern seeking, and the stage is set for coincidences to feel like synchronicity. In the end, perhaps the most honest stance is one of openness, to celebrate the timing without exaggerating causation, to honor the scientific explanations while still marveling at the universe's occasional flair for drama. We can hold the clustering lightly, neither dismissing it as meaningless nor elevating it into prophecy. The September-October convergence gives us material for both rigorous study and imaginative wonder, so long as we remember which is which. With that in mind, we turn to one of the most persistent questions born of such clustering: could space weather, in some subtle way, influence earthquakes on Earth? The next section dives into this long-debated, often controversial frontier. The real difficulty in testing potential links between space weather and seismic activity lies in teasing out true physical connections from misleading statistical patterns. Earthquakes themselves do not occur randomly. They unfold according to complex statistical distributions with aftershock chains, clusters across space, and time-dependent correlations. These intrinsic properties can easily generate illusions of association with any other variable that also fluctuates over time, including indices of solar and geomagnetic activity. Meanwhile, space weather datasets themselves display repeating cycles, autocorrelations, and bursts of clustering. Such inherent structures make them ripe for producing spurious matches with seismic records, even when no physical influence exists. To properly evaluate the hypothesis, studies must be carefully designed in advance, rather than shaped after reviewing the data. That means registering hypotheses ahead of time, defining the time frames, regions, and statistical tools to be used before the analysis begins. Blind testing methods, where earthquake catalogs are analyzed without knowledge of concurrent space weather conditions, would help reduce the risk of subconscious bias creeping into interpretation. Yet such stringent approaches remain rare in the published literature, even though they are critical for determining whether any authentic relationship exists. So what kind of evidence would be truly persuasive? First, any suggested mechanism must establish physical plausibility. That would require either laboratory experiments or robust theoretical models demonstrating that electromagnetic fields, energetic particles, or other solar outputs could meaningfully alter stress within crystalline rock at magnitudes relevant to tectonic rupture. Second, correlations would have to show predictive power, performing better than chance when applied prospectively to fresh, independent datasets, rather than only explaining past patterns. Third, if such an influence were real, it would almost certainly be conditional. Certain fault geometries, stress states, or tectonic environments might be more sensitive, while others would remain unaffected. A universal mechanism impacting all seismic zones equally is improbable given the huge diversity of geological settings and fault behaviors worldwide. The Venezuelan earthquake cluster that struck during heightened geomagnetic activity provides another entry in the long-running debate, but a single coincidence cannot establish causation. Venezuela is positioned on an active tectonic margin where magnitude 6 events occur sporadically, yet predictably, driven by plate interactions and regional stress redistribution. If space weather does play a role, it is most likely subtle, potentially advancing the timing of quakes that were already near the breaking point by a matter of hours, days, or weeks, rather than triggering entirely new ruptures out of nowhere. According to mainstream seismology, earthquake timing is dictated primarily by local stress evolution, rock and fault zone properties, and inherently stochastic processes that operate in chaotic, nonlinear systems. External factors, whether fluctuations in atmospheric pressure, geomagnetic disturbances, or other environmental shifts, are, at best, secondary and usually negligible compared to the dominant tectonic forces that build stress over decades and release it catastrophically in moments. The most scientifically honest conclusion is one of cautious openness. Minor couplings, whether electromagnetic or gravitational, cannot be completely ruled out, but current evidence shows no convincing proof that they matter on a detectable scale. Future studies would benefit from a physics-first approach, beginning with plausible mechanisms grounded in well-established physical principles, then searching for statistical validation rather than chasing intriguing correlations that may simply be artifacts. For practical purposes, however, earthquake preparedness should not involve watching space weather forecasts. Public safety depends on robust building codes, emergency planning, and probabilistic seismic hazard assessments derived from established geologic and seismic knowledge, not on speculative external influences. As we close this examination of potential Earth-space connections, an even broader speculative question emerges. Could the violent energy of stellar explosions, novae or even supernovae, leave detectable imprints on Earth's climate or geophysical systems across longer spans of time? Part Novae and Climate. The notion that explosions of distant stars might shape Earth's climate operates on scales utterly different from the short-term space weather earthquake debate. In theory, extremely nearby supernovae could exert profound atmospheric and climatic effects over geological timescale. But the ordinary novae that occasionally flare into naked-eye visibility, like V1935 Centauri and V7994 Sagittari, are dramatically weaker and astronomically remote, rendering any immediate impact on our planet's climate vanishingly small. Visual magnitude tracking, CCD-based photometry, and high-resolution imaging by skilled amateur astronomers provide the level of temporal precision necessary to capture subtle, short-term fluctuations that might align with specific space weather disturbances. The strongest precedent for such dramatic interactions between coronal mass ejections and icy bodies in space comes from earlier solar system comet encounters. One of the most striking examples remains the 2007 disconnection event of Comet Encke's tail, documented in detail by NASA's Stereo spacecraft. That event made it unmistakably clear that magnetic reconnection between solar plasma and cometary ions can violently sever a comet's tail in real time, leaving behind evidence that could be carefully modeled within plasma physics frameworks. If comparable tail loss phenomena are recorded for 3I Atlas, they would provide groundbreaking evidence of how solar magnetic structures engage with material arriving from interstellar space. Unlike solar system comets, this visitor carries volatiles that may differ in composition, ionization properties, and magnetic response. These differences could produce reconnection dynamics unlike anything previously observed, offering scientists an unparalleled chance to study plasma interactions under conditions not reproducible in laboratories on Earth. But the significance of 3I Atlas extends far beyond the realm of solar wind encounters. Locked within its frozen chemistry are isotopic fingerprints from the star system where it formed, potentially revealing how heavy elements were forged, redistributed by ancient supernova explosions, and incorporated into new planetary systems. When solar radiation heats its surface and releases these ancient compounds, humanity gains a rare opportunity to study interstellar material up close through spectroscopy, a type of natural experiment otherwise impossible to conduct. As this object journeys from the quiet, radiation-filled void of interstellar space into the high-energy, turbulent environment of solar maximum, it experiences a transition across vastly different space weather regime. That trajectory creates a natural test case for exploring how cosmic rays and magnetic fields gradually reshape the chemistry, structure, and volatile content of icy bodies over millions of years. Professional radio observatories can track its molecular emissions, shedding light on its internal temperature, spin state, and patterns of gas release as sunlight penetrates deeper into its nucleus. Advanced long-baseline radio interferometry could even help distinguish whether its core is a singular, solid fragment or a loosely bound agglomeration of rubble held together only by weak self-gravity. This timing also proves ideal, arriving as humanity's monitoring capabilities reach new levels of sophistication. Real-time solar wind data streams from multiple spacecraft, magnetohydrodynamic models, capable of simulating CME propagation, and dense global monitoring networks all create a contextual framework that was lacking during earlier interstellar encounters. Such resources mean that any behavioral shifts in 3I Atlas can be interpreted with greater clarity than ever before. In addition to its scientific appeal, the object also functions as a practical exercise in planetary defense. Although its trajectory poses no danger to Earth, its predictable brightness changes, orbital evolution, and response to solar activity provide a perfect opportunity to validate telescopic survey methods, orbital calculations, and characterization tech. These are precisely the capabilities humanity would need if a truly hazardous interstellar object ever approached. The wider implications stretch into astrobiology. If this cosmic visitor carries organic molecules or other chemical seeds of biology from its birthplace, spectroscopic studies could reveal whether the essential building blocks of life are widespread throughout the galaxy. Such a discovery would have enormous consequences for our understanding of life's potential emergence in alien star systems. The extended visibility of 3I Atlas, expected to last into early 2026, ensures these investigations won't end after its Mars flyby, but will continue through its perihelion and Earth approach phases. Critical dates stand out on the observing calendar: perihelion on October 29th, when the object reaches its closest point to the Sun, and December 19th, when it comes nearest to Earth. Both windows offer invaluable chances to capture the evolution of this visitor under escalating solar heating. As these moments approach, the rare overlap of factors, an interstellar body entering the solar system at the peak of solar cycle, supported by advanced monitoring technology and coordinated international campaigns, sets the stage for discoveries that may alter our perspective on how star systems exchange material with interstellar space. The upcoming months are filled with promise, hinting at revelations that could reshape our knowledge of cosmic processes and our role within the broader galactic neighborhood. Part 50. Looking ahead, October and beyond. Circle October 3rd, 20th, 21st and 29th in your calendars, and highlight December 19th as well. These are not just dates, they represent potential turning points in humanity's understanding of interstellar objects, solar influences, and our dynamic galactic surrounding. What unfolds on these days may begin to resolve questions that have fascinated astronomers for centuries, questions about how the universe connects across scale. On October 3rd, 3I Atlas makes its closest approach to Mars, passing at 0.19 astronomical units, about 28 million kilometers from the red planet. This marks the first documented time in history that an interstellar visitor will come within reach of orbiting spacecraft built specifically to study small bodies. Both ESA's ExoMars Trace Gas Orbiter and NASA's Mars Reconnaissance Orbiter have modified their observation schedules to capture this event. From Mars's vantage point, astronomers will gain perspectives impossible from Earth, potentially resolving lingering uncertainties about Atlas's size, shape, and activity. Simultaneous viewing from both Earth and Mars also allows parallax measurements that could refine distance and dimensional estimates far better than single-point observation. As Harvard astronomer Avi Loeb described it, this encounter is like a blind date with Mars, an unpredictable meeting between human technology and interstellar matter. The Mars Reconnaissance Orbiter's high-rise camera may achieve resolutions on the order of 30 kilometers per pixel when aimed at the object. While this scale won't reveal fine surface detail, it might differentiate between a compact nucleus and a more diffuse coma, providing critical clues about its physical structure. Still, scientific expectations must remain tempered. Interstellar objects, even at their closest, generally appear as unresolved points of light through telescopes. The most valuable results are likely to be refinements in size, reflectivity, compositional spectra, and activity levels, rather than breathtaking images of alien landscape. October 20th and 21st bring a different spectacle. Comet CSAO's 2025 R2 Swan reaches its nearest approach to Earth at about 0.26, 0.27 astronomical units. The timing is perfect, coinciding with new moon conditions and the annual Orionid meteor shower, creating ideal dark skies. Current models suggest Comet Swan could brighten to magnitude 4 Sus, making it visible to the naked eye in pristine skies and easily accessible with binoculars or small telescopes. Yet, as with all newly observed comets, brightness forecasts carry great uncertainty. It may dazzle observers with striking tails, or it could fizzle quietly. This confluence of celestial events during late October is unprecedented. An interstellar comet, a bright solar system comet, the Orionid meteor shower, and heightened space weather, all overlapping under optimal observing conditions. October 29th then marks the perihelion of 3I Atlas, when it swings to 1.36 AU from the Sun. This phase may trigger explosive releases of volatiles frozen for eons, potentially sparking dramatic brightening, unusual chemical emissions, or even fragmentation. Although it will remain outside Earth's orbit, the geometry ensures excellent monitoring from professional ground-based observatories around the world. Finally, December 19th brings its closest pass to Earth, roughly 1 point. This distance is closer than Mars at its farthest, offering astronomers months of excellent observational opportunities that Oumuamua, by contrast, never provided. Its long window of visibility into early 2026 makes it a unique chance for extended study. Expectations, however, must be kept realistic, rather than spectacular naked-eye shows. Scientists anticipate gradual brightening, subtle spectroscopic shifts, and morphological changes visible through sensitive telescopes. The true breakthroughs are likely to come not from dazzling images, but from data revealing isotopic compositions, volatile contents, and evolutionary behaviors that distinguish this body from our homegrown comets. Meanwhile, solar activity remains intense, with solar cycle 25 peaking, late 2025 and early 2026, promise heightened geomagnetic storms, auroras, and technological impact. The Russell-McFerrin effect during the equinox season further enhances the likelihood of significant space weather events, creating ideal conditions for aurora watchers. NOAA's Space Weather Prediction Center continues to track solar outbursts, modeling CME trajectories, and providing alerts for G-class geomagnetic storms, solar radiation events, and radio blackout. Back on Earth, seismic monitoring in Venezuela continues after the late September magnitude 6.2 and 6.3 events, underscoring the unpredictable but inevitable activity of the Caribbean-South American plate boundary. While speculation about space weather influences persists, earthquake preparedness still rests firmly on established geological science, building codes, and emergency planning. In parallel, nova observations press forward. Both V1935 Centauri and V1794 Sagittari continue their characteristic fade, monitored by professionals and dedicated amateurs alike. Photometry and spectroscopy, coordinated by the American Association of Variable Star Observers, help unravel the physics of these stellar outbursts, while satellites like Fermi and Swift detect high-energy emissions from shock-driven particle acceleration. Dust formation events may soon create temporary brightness dips, adding further insight into the chemistry of novae ejecta. The task now is to distinguish between real physical relationships and coincidental clustering. Each event, interstellar visitor activity, comet appearances, auroras, earthquakes, and stellar explosions, unfolds under its own physical laws. And yet, the sheer overlap of so many dramatic phenomena within such a compressed time frame is extraordinary, and documenting it provides both scientific value and a sense of cosmic wonder. This convergence may be coincidence, or it may hint at subtle interconnections not yet understood. Either way, it highlights the remarkable fact that we live in an era uniquely capable of observing, tracking, and studying such phenomena across vast scales of space and time. We may not resolve all the mysteries immediately, but what is clear is that humanity now occupies a privileged vantage point, the first generation to witness and measure such cosmic convergences in real time.